Next up is Dennis Wright. He will be updating us on our current study for this year, which is on the Tether-Climber interface.
Late part of last year, started a climber tether interface study, and I'll tell you just what that is. So I'll talk about first the reasons for and the goals of the study, and then discuss a little bit this thing we call climbability. And of course, any part of a space elevator has to include a climber. So we have a conceptual climber design to talk about. And tether properties and fabrication are very important. And finally, I'll finish up with a status of where the study is. So if you think about a space elevator, obviously the first critical thing is that you have a tether, but you're going to need something to climb the tether. Tether, it looks like we're going to have what we need in probably the near future. We have some very likely materials like single crystal graphene, that's the SCG, and hexagonal boron nitride. And it looks like they may be able to be mass produced in the near future. And so we are taking that right now as a given and proceeding on to the next thing. So we have to be able to assure ourselves that we can build something that grips onto this tether and generates enough traction to move it upward and downward. And so we wanted to try to be analytical about this as possible and try to quantify the conditions at the interface between the climber and the tether. So we're really looking at where the rubber meets the road here. And our goals are, in the study, to quantify the conditions at the interface. What are the physical parameters that apply? What's the environment between the drive mechanism and the tether? We also wanted to develop a conceptual design for the climber as a way of focusing our attention on what is important and what's not. And then finally, we need to determine the properties and the structure of the tether because that will certainly affect the interface. So what is this thing called climbability? We are essentially defining it as the ability of a climber to drive itself up and down the tether. And it covers a lot of area. So we really had to think about how to narrow the focus for the study. Obviously, if you think of all the things that affect the ability of a climber to climb a ribbon, it's a long list. And so for simplicity, we have narrowed it down to the following assumptions. We'll have a tether consisting of about 12,000 layers of single crystal graphene, which may be in combination with hexagonal boron nitride. We also assume that we would have vacuum conditions. So we are going to say that the condition we'll treat now is outside the atmosphere. We're going to assume that there is either a high stage 1 or a cable car system or something to get us through the atmosphere. We can deal with these conditions later, but we wanted to first find out, can we actually build something that climbs the climber in the majority of its distance? We decided to use a frictional drive with opposing wheels which pinch the tether. There are many other options, but that's the one that looks best. We also assumed that we would use existing technology for the climber components. Obviously, things will improve with time and we can do better. We can optimize the way the climber is built and operates, but for now, that is a restriction that we'll take. And another somewhat academic requirement is that the climber must lift at least the weight of its drive, power, and heat dissipation mechanism. So essentially, the payload has to be greater than or equal to 0. Obviously, a 0 payload is not very practical, but in terms of defining what we need to climb the tether, then this is the condition we're looking at. We want to determine the acceptable ranges then of a large number of material and component parameters. One very important one is the mutual coefficient of friction. So the friction between the tether and the climber wheels that pinch it. And looks like we need a coefficient of friction of greater than 0.1. Shear stress is going to be important too. So if you can imagine, well, I'll get to that in the next couple of slides. But shear stress is important because we want to obviously not allow the wheels to delaminate the tether since it is constructed by layers. So let's look at the conceptual climber design. We started with something like this conceptual design not because we wanted a detailed design right off the bat, but we wanted to uncover basically what we know and what we don't know. And also it will suggest improvements for the next design. So it's by no means a final design, and it looks something like this. So you have two counter-rotating wheels. There are axles that they rotate around, and we're putting compressive force, or the axles rather, cause the wheels to put compressive force on the tether, and that generates the normal force on the tether. And so obviously very simplified, we'll have to have a set of motors for each set of wheels, and some kind of ejection system, and so on and so forth. And two of our members, our group members, Larry and Ryan, have been working on the design, and they've made a lot of progress. So here is a picture from Larry of the design as it stands now. So you see, basically, you can see my little arrow, I hope. The black represents the tether, and these green cylinders represent the wheels. And through the wheels, you can see looks like a rather thick axle, but in fact, it's hollow. And the axles are driven by these silver cylinders on the edge, which are electric motors. And then we have things like these compression jacks and all sorts of other detailed systems. So our design goal then is that the climber should have a total mass of 20 tons and a payload of 14. It should make it to GEO in 8 days. And we have to use only currently available components. Now, as I mentioned, as technology goes on, we'll have probably better motors with higher power to mass ratios, maybe better materials for resisting fatigue and things like that. But we will not worry about that in this study. Now, these mass budgets may not be met, but that's really not the point. At this point, we're using those as a guideline. We can try to meet those by optimization and trading one thing off against another in future designs. So the climber design then leads to material property. As I mentioned, the coefficient of friction is critical here. We need to grip. And so it looks like we need at least a coefficient of friction of 0.1. And the way this is working then is that the axles working through the wheels provide the pressure. The pressure and the friction generates a force through a contact patch on the outer layers of the tether. And so this basically sets the minimum compressive force of the strength on the tether. Now, we've got this frictional force, which is acting basically along the length of the tether. So you have that force in that direction. And the tether has to somehow transmit this transverse force into the bulk of the tether so that we can take advantage of the material strength. But of course, the tether we think will be layered. And so we have to make sure that this large transverse force on the outer layers do not cause it to separate from the inner layers of the tether. And so this sets a minimum shear strength for the tether. Now we get into some tether properties. So let's first look at single crystal graphene. Multi-layer single crystal graphene, and Adrian is our expert on this. We look to his company to be producing large amounts of this material, and it is essentially thousands of layers of roughly 1 nanometer thick layers. It's between 0.33 nanometers and 1.3, depending on how you calculate the field extension and things like that. And we hope that they will be stacked in the way that you see in the picture. So you can probably see two layers in this ball and stick model, in which one of the carbon atoms from the layer below occupies the space in the center of the layer above, of the hexagon and the layer above. And this is the arrangement which allows the layers to get close enough together that the van der Waals forces can be significant, and we hope hold things together. So we know that single crystal graphene has a lot of great properties. So it's a high specific strength, high compression strength, great electrical and heat conductivity, high optical reflectivity, and in fact, it goes all the way across the electromagnetic spectrum. Seems to be resistant to attack by oxygen radicals, so it's good in the atmosphere. However, it looks like it has a low coefficient of friction, so between maybe 0.05 and 0.1. And you recall I said that we need 0.1 or greater. And it's possible because the bonds within the layer are covalent and very strong, and the bonds between the layers are van der Waals and probably quite a bit weaker. In fact, sometimes about a factor of 1,000. Then the natural question to ask is, what is the shear strength when we have this in layers? Now, another material is hexagonal boron nitride. So you can see a picture here with the blue being the nitrogen and the pink being the boron. So pretty much the same design or same structure as single crystal graphene, except you have different elements. And it has a big advantage of this material. It has a much higher coefficient of friction, so about 0.23. It's almost as strong as single crystal graphene, but a little bit lighter. And so it could be an alternate material for the tether, but maybe more importantly, it's got high friction and it's an insulator. So this may be something we need, whereas single crystal graphene is a very good conductor. It looks like boron nitride would be an insulator. So we could conceivably use HBN for the main tether material, but maybe it's best to use it for the outer layers of the tether. So we could have a tether whose bulk consists mainly of single crystal graphene with a few layers on the outside consisting of boron nitride. And such a tether would be about 1 meter wide and 12 microns thick. So the latest manufacturing methods for polycrystalline graphene, so this is not single crystal, but polycrystalline, are getting faster and faster. So there are companies out there today who are producing it at meters per second or meters per minute rates, and we expect that to get bigger and bigger or faster and faster. So this is encouraging, even though it's not the actual material that we want, but it is encouraging that we can do the same thing with single crystal graphene, which we'll definitely need to do. So how do we put these layers together? So there are some speculative ideas that we've talked about in our study. And one very neat idea that Adrian proposed is that we can use high pressure to create the normal bonds, that is the sp2 hydride bonds in single crystal graphene, to convert to the sp3 bonds between layers. And sp3 bonds are basically the bonds that you find in diamond. And so if we locally put high pressure on the laminations of the tether, we could perhaps press them together, force some of the bonds to be diamond bonds, and then we can increase the resistance to shear stress. So that's a really nice idea, but it really needs more exploration. The other way is to, perhaps we don't need hydrogen or hexagonal boron nitride. Perhaps we can stay with the single crystal graphene, but adsorb hydrogen on the graphene. This option would increase the friction, and then we could stick with one material. Another thing we could do is sort of wrinkle or crepe the material in some of the layers, and that would also increase friction. But we've identified a major sub-study, I guess you could say, within the study of molecular modeling. So we're really going to need to verify that we can even do the spot welding or to understand the hydrogen adsorption and things like that. We need to do molecular modeling, and we're in the process now of identifying software that can do that. And finally, we get into some testing. So there are lots of companies, well, several, and an increasing number of companies now producing various forms of graphene and boron nitride. As I mentioned, the graphene produced now is polycrystalline for the most part and not single crystal. But the polycrystalline graphene would be a very good proxy for us for developing the testing methods that we need. So what do we do here? We need to identify all the material parameters that we need to know. So it's a big list. And then determine acceptable ranges of a large number of materials and component parameters. And I mentioned just a few of those, that is the friction and the shear strength and the compression strength values. Another thing we can do as an outgrowth of this study is to continue to act as a kind of an information broker between the material producers and the people who would do the testing. So some companies will be the producers, perhaps some labs at universities would do testing, and we hope to be the ones that suggest what needs to be measured. And to finish up, where are we in the study? I mentioned it began late last year. The conceptual design, as you can see by the diagram, is proceeding very well. We definitely have a deeper understanding of what material parameters are going to be important for us. The climbability formulation remains a challenge. There's been some work on this, but we're aiming for a mathematical relationship between the critical parameters. And this is pretty complex. Martin Lades is working on this now and making some excellent progress. Needs more study, but that will be part of our final study report. And essentially, because of the new study areas that we've uncovered, the interface study will probably take a little bit longer than a year, perhaps 18 months. But out of that, we expect a lot of new material. That's all for me.
Thanks, Dennis, for that update. We really appreciate that. And as Dennis said, please make sure you get into contact with us if you want to be a part of the next study.